Welcome back. Let's use dynamic programming and memoization to improve this function. Just like we did when we learned about memoization, this is fairly simple. Let's remove this for now. I'll keep this at the top. And in here, create a new function. We'll call it Fibonacci master. This function will have a cache, a hash table, or an object to store our pre-calculated answers. And if you remember, because we want to make sure that we don't reset this every time we run this function, we're going to return another function inside here, again, using closures in JavaScript. And in other languages, you might have to use different techniques. And in here, we can just have a function. We can name it whatever. Let's call it fib. That takes n. That is the number we give it. And inside here, well, we do something very similar to the above, except we're going to check the cache first. We're going to say if n is in cache, just like we did in the memoization videos, and we're going to check if the cache exists. And if it does, we're going to return cache n. The first time around, this is going to be empty, so it's not going to work. It's going to go into the else condition. And in here, we have two conditions, just like we do up here. If n is less than 2, then we need to return n, just like we did above over here. Otherwise, we run our sequence. So we do fib of n minus 1 plus fib of n minus 2. But we want to store this value in our cache. So we're going to say cache n is going to equal the result of this. And finally, we want to return this value because we are using recursion here, and return cache of n, which we've just set. And that's it. That wasn't that hard, right? I mean, we have a few extra steps, but all we did was just add the result to our hash table. So that now, if I do const, let's say faster fib is going to equal to Fibonacci master. Remember the first time around, we're going to run this function and create the cache variable. Whoops, let's try that again. And create the cache variable, and it's going to just return this function. So it's similar to just saying like that, faster fib equals this function now. Except that now we have access to the cache variable. So that now I can console.log, and let's call this DP for dynamic programming, and we'll say faster fib and give it, let's say, 10. If I run this, I get 55. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 55. That's pretty good. But let's do something fun here to see if it works. This calculations tally that we used in Fibonacci number, let's move it to the Fibonacci master. Or instead of here, down in this function, because this is the one that we were recursing over. And let's see how many times this calculation happens. If I run this, oh, and we need to console log these calculations. So at the bottom over here, let's have a console.log. And we'll say we did calculations, just like that. So that if I run this, we see that we did 19 calculations with the Fibonacci master when we entered 10. Versus if we move back calculations up to here, to our old version, oh, and we actually have to run this function. So in here, let's just have console log so we can have everything clean. We'll say console.log. This will be called slow, and it will be called, what was it? Fibonacci. So we'll just do our original function, Fibonacci, with 10. So let's see and run. We got the same answers, 55, but it took us 177 calculations to get to 10. Holy moly. So 19 versus 177 calculations. And if we do 20 here, well, we have that many calculations. And actually, let's just do 35. See if that's possible. Let's see 35. There you go. Look how many calculations we had to do. Versus if I do 35 with our memoized function, move the calculations in here. And we run this. 69 calculations. That's it. Instead of before, where if I entered Fibonacci 50 here, it would actually crash the browser because we would do so many calculations. With this one, I can do Fibonacci 100. And I have no problem. Look how fast it calculated that. That's pretty amazing. It only did 199 calculation. I hope you see the power of dynamic programming. And it's not that hard, right? All you need is to remember this pattern. And if there's any repeated calculation, to just memoize the result of a function. So that if the parameter is the same, we check in the cache first for the result. But let's talk about space and time complexity here. This, well, because we're only doing the necessary calculation, in this case, all our calculations, well, are n, right? We do 1, 2, 3, 4, 5, 6, 7 calculations versus all the ones that we did before. So that our time complexity for this one is O of n. Versus with this one, that was O of 2 to the power of n. Just like that, we made huge savings. The one drawback is that, well, we increased the space complexity, right? I mean, with the first Fibonacci number, we had to add functions to the stack. And these functions, the deeper it is, we added to the stack. But once we got to the bottom, we popped off the stack so that the stack was as deep as the tree. But with the memoized version, we also have this new variable, this cache hash table that we have to store our memory in. But as we know, we sometimes need to trade off space complexity for better time complexity. And this is what we're doing in this case. And in this case, the time complexity savings are very large. All right, I hope I got you excited about dynamic programming. It's very interesting and not as overwhelming as you think, right? I'll leave a couple of problems for you to do to get used to dynamic programming, but I recommend that you take the code that I'll leave here for you and you can just grab it from resources and play around with it. Otherwise, I'll see you in the next video. Bye-bye.